taking a look at differentiation by parts, better known to us as IBP, or integration by parts. And this is section 7.3 for us. I did have a review scheduled, but let's skip that while we're on the video and just get into the method of integration by parts. And it'll allow us to integrate integrals that are like natural log x or e to the x, x squared cosine x, things that U sub does not work for. We've worked with trig substitution and trig inverse integrals, but those methods would not work for this. So here comes along integration by parts. And with integration by parts, this is the basic layout for integration by parts. And as you can see, we're going to identify out of our integral two parts. One we'll assign to be u and one will assign to be dv. So when I'm looking up here, you can tell that there really were two functions. Now here it doesn't look as apparent that there's two functions, but you can consider e to the x one of the functions and dx our other function. Rules for selecting the u and the dv. For the dv, I want to select the most complicated part of the integrand that can be readily integrated. So I'm going to choose the most complicated part. So looking up here, which one is more complicated? And you can select that to be your dv. And then for u, I want to select something that becomes simpler when differentiated. So for instance on here, I might select this to be my u because I know when I take its derivative, it does become a little bit more simple. And added to that fact, this would make dv then, and I can actually integrate the cosine. It becomes sine x. Okay, so just to give you an idea, sometimes it's nice to use this little memory device, the Lie8 plan, and we talked about this last year, I believe, for selecting your u. The natural logs are a good thing to let be u because I can take its derivative, but actually integrating a natural log can be difficult. And inverse trig functions would be my next selection for u. This is for selecting u, so you might want to put that down as well. And algebraic expressions like polynomials. Trig functions, sine, cosine, tan. And then finally e for exponentials. That gives you some sort of hierarchy in your selection process and maybe will make it a little easier. Whoops, bumped ahead. So we have x e to the 3x. Rules for choosing u and dv. Possibilities for dv. I could select the x. For the dx, I could select x, dx. I could select e to the 3x dx. Notice we're always selecting the dx with it because we're going to integrate it with respect to x then for the dx. On this particular one, if I think about the Lie8 plan, I am looking at an exponential and I'm also looking at an algebraic. Well, algebraic is suggested to be our selection for u. So let's let u equal x. And our dv then will be e to the 3x dx. On the u, what I'm going to do is create my du. And the derivative of u becomes 1 du. And the derivative of x is 1 dx. On the other side, I need to go back upwards and integrate. So I'm going to integrate on this side. The integral of e to the 3x, well, it is itself, so e to the 3x. And then, because it's not just a plain x up here, I will have a little bit of a chain rule once I take the derivative of this. And since there is not a 3 down here, I will need to put in this 1/3 so that it corrects my derivative, the chain rule. Now, setting this up, the theorem goes u times v minus the integral of v du. So I really just need to follow the pattern. U times v, and sometimes I just think, well, I'm going to come across here, so I got x times 1/3 e to the 3x. And then the next thing I do is I take v times my du. So then I kind of think of my diagonal here. Now I'm going to minus the integral of v du, 1/3 e to the 3x dx. I'm just substituting in those parts. Now, on this one, I don't need to do anything with this very first term. It does not need integration. It's already just situated there. The next one, I have this 1/3. The integral of e to the 3x is e to the 3x multiplied by 1/3. Just like we had done here. We had already talked about the integral of that. And this creates our answer. We could make it, probably simplify it a little bit. And for that, I think I'll bring a 1/3 e to the 3x out front. That'll leave me an x minus 1/3 plus my constant. Next, let's look at x cosecant squared x. Well, once again, I have trig function and algebraic. And if I think of Lie8, it suggests to us that why don't you try x as your u? So I can let this be u and this be my dv. And over here, let's let this be x. The derivative will then be dx. du equals dx. Our dv, we're saying let it be cosecant squared x dx. And is it possible to integrate that? Indeed it is. The integral of cosecant squared x is cotangent x. And it will have a negative with it. So that when I take the derivative, just double check your work. When I take the derivative of cotan will be negative cosecant. But luckily, I had my negative there, and the negative flips this back to positive. So we do get our dv that we expected. Once we have that, now we can go in and solve this problem. The integral of x cosecant squared x dx is equal to u times v. That'll give me x times negative cotangent x minus the integral of v times du, and that's going to give me a minus, so plus cotan x dx. The first part we don't have any problem with. That's set, isn't it? Now we just have to figure out what is the integral. And you know, it's one of those that you have memorized in the past. I'm going to suspect that it could be just a little bit foggy to you. Natural log of sine x plus c. And if you would have gotten stuck on a test, I probably would have come back to the fact that cotan can be written as cosine over sine x dx. And then with a little bit of u sub, let u equal sine x. Its derivative is cosine x dx. This is du, isn't it? And then I could set this up as 1 over u, and dx gets substituted, cosine dx gets substituted with du. And from there you can see it's natural log absolute value sine. Okay, so we've got that done. Third problem, the natural log. And you're probably asking yourself, I only see one function. But no, there really are two functions. So out of this, we need to set one of them as u and one as our dv. It is a natural log. So the suggestion is to let natural log be our u and dx be our dv, which totally makes sense because if I would have made natural log dv, I'd have to integrate it, and that's what I'm trying to do, and that's where I'm stuck. So let's create our own little box. Let u equal natural log x, has a nice integral. It's 1 over x dx. Please make sure you put the dx on your labeling there. Then the next thing is, let's start with dv. dv is dx. And integration will give us the integral of dx, just think of it like that, will be just x. Now, to take the integral of natural log x dx and set it up, u times v will give me x natural log x minus the integral of v times du, x times 1 over x dx. Simplify, we get x natural log x minus the integral of dx. Continue on our path here, and we get the integral of dx is x plus c. Final answer. It is one that you could memorize if you want, but it's actually a pretty easy integration by parts process too. Did I skip over one? There we go. So I'm going to go ahead and do this one in the tabular method because we did practice that tabular method last year. And the tabular method works very, very well when I have an algebraic function that I can set up to be my u. So the tabular method, when u is equal to like an algebraic expression. Because what we need to have happen is our column that we're assigning to be u, which I'm going to say let's let it be x squared, needs to eventually zero out. So if I take my derivatives, I march on down through and eventually I hit 0. That is a very good problem then to set up as the tabular method. Then I need to set up my dv column, and I'm going to start out with e to the 4x. And now this whole way down I am integrating each of them, right? So the integral of e to the 4x is e to the 4x, correction of a 1/4 out front. Then the integral of that becomes e to the 4x, and I had the 1/4, but when I integrate this, I need another 1/4. So this indeed turns out to be 1/16. Next, integration. Integration of the e to the 4x will give me 1/4 e to the 4x times 1/16 makes this 1/64. Now I can stop once I reach the same level as that 0, 1 did. And if you have line paper, it's probably going to be a little bit easier to follow. Okay, now how do I put this all together? Well, I connect the first u with the integral of dv. So it becomes u times v, doesn't it? Just like when we're doing integration by parts. This starts out with a positive, and then the next one, I draw my arrow. This one will have a sign that is negative, and then this one, the product we want to be multiplied by a positive. And if you recall, you liked these. This equals 1/4 x squared e to the 4x minus because I'm picking up this negative 2x over 16 e to the 4x. Then the next one I multiply by a positive, and I'll have 2 over 64, which I could simplify e to the 4x plus c, and let's just do one cleanup step, reducing those fractions. X over 8, e to the 4x plus e to the 4x over 32 plus our c. Tabular method, a nice method to use. For this one, can I select or can I use the tabular method? Well, the answer would be no, based on the fact that if I set this up to be u, its derivative will just continue to be e to the x, never reaching 0. On the other one, cosine, well, cosine cycles, if I decide to let it be u, it cycles back and forth as well, doesn't it? It would be sine, and then it'd be negative cosine, and then it would be positive negative sine. I think I got that right. Oh, no, I was thinking integrals, wasn't I? Derivative of sine gives me Derivative of cosine gives me negative sine. Now we're on to it. Negative sine gives me negative cosine. Derivative of negative cosine gives me positive sine. And then it starts all over again. Derivative of sine gives me cosine x, and then I'm kind of back wrapping around again. So they do cycle in patterns of 4. So that's a bummer. We can select either one, to be honest, on this as our u and du. I'm going to go ahead and let this be my u and let this be my dv. So let's let u equal e to the x, and then du will be equal to e to the x dx. Nice integral, nice derivative. Doesn't get any more complicated. Doesn't really get any simpler, but on the cosine x dx, if I integrate that, I get v equals the integral of cosine is sine x. And I was able to integrate either of these choices. That's why you could really select it, the u, to be either of those two functions. Now, let's do our integration by parts. This will equal u times v minus the integral of e to the x cosine x dx. And maybe this is starting to come back to you because we looked at these last year. They cycle back. And let's set up a new u sub, but we must maintain the same u that we had originally started. So u equals e to the x. Its derivative will be e to the x dx. That forces dv then to be cosine x dx, and the integral of that will be sine x dx. I feel like I messed up. I did. This should have been sine all along. And that'll force this to be reversed. Sine x, and then the integral of sine is cosine x with a negative. Now, the first term there is fine. The integral of e to the x is going to be u times v minus the integral of v du. So u times v gives me e to the x times negative cosine x minus the integral of negative cosine x e to the x dx. That'll turn into a plus, and then let's send that negative through e to the x sine x plus e to the x cosine x minus the integral of cosine x e to the x dx. And if you notice, on my left side and my right side, bringing this down, I have the integral of e to the x cosine x dx, which is a match. So we'll bring like terms together by adding it to both sides. Giving us two integrals of cosine x e to the x dx. and that is equal to e to the x sine x plus e to the x cosine x. Finally, last thing we have to do is divide everything by 2. Let's just, yeah, we'll just do that. Divide by 2, and we have our answer. The integral of cosine x e to the x dx is equal to 1/2 e to the x sine x plus e to the x cosine x. I think this will give you enough that you can take and do the homework that follows. Good day. Stop.